Section: Introduction. In this section, we discuss the recent advancements in large language models, LLMs, and their impact on research and industry. Over the past 2 years, we have seen that increasing the size of these models leads to better performance, but training them requires significant time, energy, and financial resources. For instance, Llama 3 with 405 billion parameters was trained on 16,000 H100 GPUs for 54 days, and GPT-4, with around 1 trillion parameters, needed immense computational power. This situation highlights the urgent need for more efficient training methods. We recognize that model quantization is a promising approach to reduce training costs. By using low-bit arithmetic, we can save memory and speed up computations. Traditionally, LLM training has relied on full precision or half-precision formats, but quantization allows us to use lower precision formats like 8-bit or even 4-bit. Recent hardware advancements, such as NVIDIA's H100 and upcoming B200 GPUs, support low-bit arithmetic, enhancing computational efficiency. The Hopper series GPUs, for example, offer a twofold speed increase with FP8 tensor cores compared to FP16. The Blackwell series further extends this by supporting even lower precision formats, potentially doubling throughput. While studies have shown the effectiveness of FP8 tensor cores for training, the use of FP4 tensor cores remains an area for further exploration. We face significant challenges when using 4-bit formats for neural network training, as quantizing LLMs to such low precision often leads to a drop in accuracy. This is mainly due to the limited dynamic range of low-bit formats, which increases the risk of overflow and underflow. Even 8-bit quantization methods can result in accuracy loss, making 4-bit quantization particularly difficult since it only allows for 16 distinct values. In our study, we propose a novel framework for training language models using the FP4 format, validating the feasibility of this ultra-low precision representation. To address the quantization errors in weights and activations during training, we introduce several optimization techniques. First, for weights, we develop a differentiable quantization estimator to enhance gradient updates in FP4 computations. We analyze how quantization affects the forward and backward passes of the neural network and create a function with correction terms for better gradient estimation. Second, for activations, we implement an outlier clamping and compensation strategy to manage outlier values that often occur during LLM training. By examining activation distributions, we introduce a clamping method and a sparse auxiliary matrix to maintain quantization accuracy and model performance. We conduct extensive experiments showing that our FP4 training framework achieves accuracy similar to models trained in BF16 or FP8 formats with the same hyperparameters. Using the FP8 tensor cores of NVIDIA H100 GPUs to simulate FP4 computations, we train LLMs with up to 13 billion parameters and 100 billion training tokens, with only a slight training loss gap. In zero-shot evaluations on downstream tasks, models trained with FP4 perform competitively against BF16 models. We expect even better performance with next-generation hardware like NVIDIA's B-series GPUs. To support future research and adoption, we will open-source our training code. In the preliminaries, we explain that according to the IEEE 754 standard, a binary floating point number consists of a sign bit, exponent bits, and mantissa bits. This is typically represented as xmi, where x and y indicate the number of bits for the exponent and mantissa, respectively. For example, FP16 uses E5M10, and BF16 uses E8M7. FP8 has 2 variants, E4M3 and E5M2. In our work, we use the E2M1 format for 4-bit representation, which has 2 bits for the exponent and 1 bit for the mantissa. Unlike integer quantization, floating point quantization has uneven intervals and a larger dynamic range. To quantize a high-precision tensor like FP16 to FP4, we use the ABS max method, where the maximum absolute value in the FP4 format is calculated, and a scaling factor is applied. The quantization function is implemented using a lookup table in a custom CUDA kernel, as the FP4 format supports only 16 distinct values. More details on the format and quantization implementation can be found in the appendix. Section Summary. In this section, we discuss the challenges and advancements in training large language models, LLMs, using ultra-low precision formats like FP4, highlighting our proposed framework that employs optimization techniques to mitigate quantization errors. Our experiments demonstrate that models trained with FP4 achieve accuracy comparable to those trained with higher precision formats, paving the way for more efficient LLM training. Section: Methodology. In this section, we describe our methodology. In a standard linear layer of a transformer, we compute the output as the product of the activation tensor and the weight tensor. To utilize FP4 tensor cores effectively, we need to quantize both tensors to FP4. However, directly quantizing them can lead to significant errors. To tackle this, we introduce two methods: a differentiable gradient estimator for weight tensors and an outlier clipping and compensation method for activation tensors. For the differentiable gradient estimator, we note that quantization functions are non-differentiable, which complicates gradient flow during backpropagation. The common straight-through estimator, STE, assumes that the gradient of the quantized tensor is the same as that of the original tensor, but this can lead to inaccuracies in low-bit scenarios. To improve this, we propose a differentiable gradient estimator, DGE, that reduces estimation errors while maintaining efficient forward computation. When we quantize the model weights using a non-differentiable function, we compute the backward gradient for a linear function with quantized weights. During backpropagation, we calculate the loss gradient with respect to the weights and activations using the gradient from the next layer. The chain rule helps us express the weight gradient, where the derivative of the quantization function is element-wise, resulting in a diagonal matrix. This structure simplifies our gradient computation to an element-wise multiplication. However, since the derivative of the quantization function is mostly zero, we face vanishing gradients, which can hinder weight gradient computation. The STE addresses this by assuming the derivative is 1, effectively bypassing the issue. To achieve more accurate gradient calculations, we suggest approximating the quantization function with a suitable differentiable function, calculating its derivative, and incorporating it into our equations. We illustrate this approximation with a function that simulates quantization behavior. As we increase a parameter that controls the approximation, the function becomes sharper and more closely resembles the original quantization function. We also cap the magnitude of the derivative to prevent excessively large gradient values during training. In practice, we integrate the differentiable gradient estimator into our training process. We use the hard quantization function for the forward pass to maintain computational efficiency, while applying a correction term derived from our method during the backward pass to refine the weight gradient calculation. Further details and proofs of the DGE method are provided in the appendix. Section Summary. In this section, we propose a differentiable gradient estimator, DGE, to improve gradient computation during backpropagation in quantized transformer layers, addressing the inaccuracies of traditional methods like the straight-through estimator. Our approach maintains computational efficiency by using hard quantization in the forward pass while applying a gradient correction term in the backward pass to reduce estimation errors. Section: Outlier clamping and compensation. In this section, we discuss the challenges of quantizing activation tensors during LLM training, which are more complex than quantizing weight tensors due to the presence of outliers, values that are much larger than others. These outliers can distort the dynamic range, leading to many values being rounded down to zero after quantization. To tackle this, we introduce the outlier clamping and compensation method, OCC, which limits the range of activation tensors to reduce this underflow issue. We identify outliers by searching for values with the largest absolute magnitudes and clamp them to a set threshold. Using a predefined quantile, we can express this clamping function. We illustrate the effects of quantization with and without outlier clamping using real activation data from the Llama 1.3b model after extensive training. Our method significantly lowers the mean squared error between the original and quantized tensors, improving quantization quality and maintaining training stability. While clamping reduces quantization error, it also introduces some error by ignoring outlier values. To counter this, we use a sparse outlier matrix for compensation. In our experiments, we set the clamping threshold quite high, resulting in a sparse residual matrix with only a small percentage of non-zero elements. We process the clamped matrix using FP4 GEM and handle the residual with high-precision sparse matrix multiplication. We provide a quantitative analysis of cosine similarity, mean squared error, and signal-to-noise ratio between the original and quantized tensors, showing that outlier clamping enhances both cosine similarity and signal-to-noise ratio, while compensation further reduces quantization loss. However, lowering the quantile threshold increases compensation, which creates a trade-off between computational efficiency and numerical accuracy. Next, we evaluate our FP4 training framework across various language models. We detail the implementation, including model architecture and hyperparameters. We focus on 4-bit quantization for general matrix multiplication, GEM, which constitutes a large portion of the computational workload, especially in larger models. In our approach, we quantize the activation tensor token-wise and the weight tensor channel-wise to align with matrix multiplication logic. Since FP4 tensor cores are not available, we validate our performance using NVIDIA H-series GPU's FP8 tensor cores, which can accurately simulate FP4's dynamic range. We perform non-GEM operations at higher precision to maintain accuracy and use FP8 format for gradient communication to save bandwidth. We adopt the Llama 2 model architecture and train from scratch using the DCLM dataset. We keep hyperparameters consistent across different precision settings for a fair comparison, following a warm-up and cosine decay schedule for the learning rate. We also specify special hyperparameters for the FP4 method, including a differentiable gradient estimator and the quantile for clamping and compensation. Our input sequences are fixed at 2048 tokens, with a batch size of 2048, totaling around 4 million tokens. Section Summary. In this section, we introduce the outlier clamping and compensation (OCC) method to improve the quantization of activation tensors during LLM training by clamping outliers to a predefined threshold, which reduces quantization error and enhances training stability. We also implement a sparse outlier matrix to compensate for the error introduced by clamping, balancing computational efficiency and numerical accuracy while demonstrating significant improvements in tensor fidelity through our experiments. Section: Main Results. In this section, we validate the effectiveness of our FP4 training framework by comparing it to the commonly used BF16 mixed precision training method. We present the training loss curves for Llama models of different sizes, 1.3 billion, 7 billion, and 13 billion parameters, trained with both BF16 and FP4 precision. All models were trained on the same dataset of 100 billion tokens using identical hyperparameters. The loss curves for BF16 and FP4 are quite similar, although FP4 shows slightly higher training losses. Specifically, after training, the losses are 2.55 for FP4 versus 2.49 for BF16 for the 1.3 billion model, 2.17 for FP4 versus 2.07 for BF16 for the 7 billion model, and 1.97 for FP4 versus 1.88 for BF16 for the 13 billion model. We also evaluate the models on various downstream tasks without any prior training, using datasets like ARC, BoolQ, HellaSwag, and others. The results, obtained through the LM Evaluation Harness Library, show that models trained with FP4 perform competitively in intrinsic in-context learning. For models of the same size, the average accuracy of FP4 trained models is similar to or slightly better than that of BF16 trained models. Additionally, we observe that larger models tend to achieve higher accuracy with the same amount of training tokens. These findings indicate that FP4 training, despite its lower precision, achieves performance nearly equivalent to BF16 in terms of training loss and task accuracy, making it a promising method for efficiently training large language models. In our ablation study, we break down our findings to better illustrate the advantages of FP4 training. We conduct all experiments on the Llama 1.3 billion model, using 10 billion tokens from a subset of the DCLM dataset. To speed up convergence for this smaller model, we reduce the batch size from 2048 to 256 while keeping other hyperparameters consistent. We first examine the impact of precision. The training curves for various precisions, including BF16, MSA-MP FP8, Transformer Engine FP8, Direct FP4, and our FP4 method, show that the two FP8 methods and our FP4 approach maintain pre-training accuracy, while Direct FP4 results in a significant loss gap. Next, we look at weight-only 4-bit quantization. We compare our differentiable gradient estimator, DGE, method with direct quantization. The results indicate that the DGE method significantly improves convergence, and direct quantization of weights into 4 bits does not lead to a large training loss gap, suggesting that weights are easier to quantize than activations. We find that a larger hyperparameter value can better model the quantization function but may also introduce instability. A moderate value of 5 yields better final performance. For activation-only 4-bit quantization, we assess our outlier clamp and compensation (OCC) method against direct quantization. The results show that directly quantizing activations in FP4 leads to loss values becoming undefined after a certain point in training. Our OCC method effectively reduces this loss gap, highlighting the importance of managing outliers in quantization. We also explore the hyperparameter for compensation, finding that while a higher value improves accuracy, a value of 0.99 strikes a good balance between performance and computational efficiency. Finally, we note that the granularity of FP4 quantization is crucial. While FP8 training can achieve sufficient accuracy with coarse-grained quantization, we find that tensor-wise scaling in FP4 introduces significant errors. To mitigate this, we implement vector-wise scaling, using token-wise quantization for activations and channel-wise quantization for weights. We observe that applying coarse-grained quantization to activations results in more significant accuracy loss than applying it to weights, confirming that activations are more challenging to quantize. Section Summary. In this section, we validate our FP4 training framework against the BF16 mixed precision scheme, finding that while FP4 exhibits slightly higher training losses, it achieves comparable or superior performance on downstream tasks across various model sizes. Our ablation studies further reveal that effective quantization methods and careful handling of outliers are crucial for maintaining model accuracy, highlighting the potential of FP4 for efficient training of large language models. Section: Related work. In this section, we discuss related work on quantized training and inference for large language models, LLMs. We focus on fully quantized training, FQT, while most previous research has utilized mixed precision training to speed up model training without sacrificing accuracy. Although earlier studies mainly targeted convolutional and deep neural networks, recent findings show that low-bit mixed precision training is also applicable to LLMs. For inference, research has primarily concentrated on post-training quantization, PTQ, and quantization-aware training, QAT. PTQ quantizes pre-trained models directly, while QAT fine-tunes or pre-trains models to enhance low-bit inference performance. Our approach differs from QAT, as we prioritize accelerating the training process while maintaining performance, rather than just improving inference efficiency. We note that recent advancements in PTQ and QAT have successfully implemented 4-bit, 2-bit, and even 1-bit quantization for LLM inference. However, these methods often require additional computations, such as fine-tuning calibration sets and searching for quantization parameters. In the realm of FQT, Earlier studies applied a 4-bit format to convolutional neural networks, and while some proposed frameworks for LLMs, they lacked thorough validation. Our work is unique in that we introduce a fully validated FP4 training framework specifically for LLMs, designed to work with next-generation hardware like NVIDIA's B-series GPUs. Regarding differentiable quantization, we take a different approach by using a fixed quantization function instead of relying on learnable parameters updated through backpropagation. This allows us to change the gradient estimator efficiently during training, making our method more suitable for hardware acceleration in large-scale training. When it comes to handling activation outliers in LLMs, our method stands apart from existing strategies that mainly focus on inference. We address channel-specific activation outliers dynamically during real-time training, avoiding the need for separate calibration datasets, which is essential for efficient pre-training of large models. However, we acknowledge a significant limitation. The lack of dedicated FP4 tensor cores in current hardware prevents us from measuring the full potential for speed and energy efficiency gains with native FP4 support. Our experiments rely on FP4 simulations, which add computational overhead and extend runtime. Additionally, due to resource constraints, we have not yet tested our methods on extremely large-scale models or datasets with trillions of tokens, making scalability an important area for future research.